All right, let's talk about interactions. So interactions, this is chapter 6. We've gone over one of the biggest chapters in the book, which is chapter 5, and that covers that covered the Klein-Gordon equation, and the Lagrangian, the Dirac equation, and the Dirac-Lagrangian, and the Procla equation, and the Procla-Lagrangian. That was the biggest chapter in this book, I believe, is chapter 8, where it talks about quantum fields. Okay, so we've gone over the classical fields. We have yet to go over the quantum fields, but before we go over quantum fields, we have to do two things. We have to cover classical interactions, and then we also have to cover a review of quantum mechanics. Okay, and those two are going to be the next two chapters that we're going to go over. So let's go ahead and get started here. There's going to be three types of interactions that we're going to be concerned with in this. And those three interactions are going to be, or actually two interactions, sorry. I'm thinking of three fields. There's going to be two interactions. There's going to be gauge interactions, and there's going to be Yukawa interactions. And there's actually also going to be self-interactions that we're going to cover. So there's three different types of interactions. And let's cover these really quickly. So this is interactions. And we're going to start off, so here's the brief little map of what we're going to cover. We're going to have gauge, we've talked about gauge fields. We've talked about spinor fields. And we've talked about scalar fields. Okay, and we want to consider now what the interactions are between these. Okay, so between gauge fields and scalar fields, we're going to talk about gauge interactions. So there's okay, and between gauge fields and spinor fields, there's also gauge interactions. And between scalar fields and spinor fields, we're going to have Yukawa interactions. And this is sort of the map of what we're going to cover in this chapter. So let's get into this a little bit more. Before we get into this, I would actually want to give a little bit of a primer on interactions. Sort of the philosophy of mathematically, how do we describe interactions? We're going to describe interactions in terms of these things called Green's functions, okay? And these Green's functions are going to be solutions to the equations of motion, that are given to us by the Klein-Gordon equation, Dirac equation, and so forth. When there are going to be solutions in the case when these equations of motion give us a delta function. So we're essentially describing a particle in these fields as being a delta function in these fields, okay? So let's talk about the idea behind this really quick. So suppose we had a field, okay, I'll do that a little bit better. So here's, again, I'm drawing this out like I normally always do. I have this field, and at every point in the field, like we've had up until this point, what we've been talking about, scalars, spinors, vectors, you can talk about tensor fields and so forth. But when it comes to actually describing a particle, when it comes to actually saying, what is it that, how can we actually describe a particle in this field? Right? We have these fields that are described mathematically by scalars, spinors. These are sort of what distinguish the fields from each other. But how do we describe an excitation in this field? Right? An excitation in these fields needs to come in some form, and the excitation in these fields is what manifests in the real world, right? So when you look at something like a plant or a book, these things they contain electrons in them, right? Because they have atoms, and atoms have electrons. And electrons, we're saying, are excitations in these fields, okay? So we can consider at some point in this field an excitation that maybe looks like this, okay? Maybe we have another excitation that looks like this. And then we have one here that looks like this. Okay. So in this field, okay, this, say, is a scalar field, or say it's a spinor field. And the spinor field can be excited at different locations in space. And those excitations, and the question becomes, how do we describe these excitations mathematically? Well, these things look like delta functions. And that's how we're going to describe them. Delta functions are extremely, extremely important when it comes to understanding the actual manifestation of these fields in the real world. This is an extremely interesting and important philosophical question if we were to actually dive deep into quantum field theory. And so we can get right into this. Before I actually get into this, I also want to talk about scalar fields. We're also going to be talking about self interactions on scalar fields. And we'll talk about those later. So how do we want to start here? We want to start off, again, by just considering our Lagrangian for a scalar field. So our Lagrangian for a scalar field, again, looks like this. d mu minus m squared phi squared. But now, when we throw these delta functions in here, fundamentally what's happening is we're changing the potential. That the field, a free field, is a field that has one particle in it, right? And it's affected by nothing else around it. Well, that's boring, right? We've been talking about that for like the past, 10 or so lectures or videos when we're talking about free fields and no interactions taking place. But now we want to talk about interactions. So when we talk about interactions, we want to add a potential term here. And this potential term is going to help us in understanding exactly what the dynamics have to be when we have electrons within the vicinity of other electrons, for example. Okay. And so simply put, we can use we can use this again. This is the Euler-Lagrange equations. Euler-Lagrange equations minus this is minus d mu dl d by d mu phi equals 0, right? So if we were to do that, again, if we consider just this one again, well, this is just going to be, this is going to be 1/2 times 2 times m squared times phi squared, or no, not squared, just phi, plus our dv d phi, because again, v is a function of phi, not the derivative of phi. And then as we've seen before, this other term is going to give us the kinetic term. And again, the kinetic term, as we've seen, was d mu phi, like this. So what does this mean? This means that, let's see, we can cancel out these 2's here, and that's actually a minus sign. So what that gives us is minus m squared phi plus dv d phi equals d mu phi, like this. Let's take a look at this now, because if we were to rearrange this, again, we just get d mu phi plus m squared this is actually a minus sign. That's why I'm getting mixed up here. Right? This is a minus sign, times phi, and that equals d phi, like this. And then we could say that d mu phi minus m squared phi is equal to, we're just changing the signs, dv d phi. Okay. And so again, we've seen this before. We've seen this, the derivation from this to this, using this up here. We've seen that before. So I'm skipping a few steps. You can go back to the video that describes that. I believe that was like within the first 2 videos talking about chapter 5. And what you get is this. So once we get to this point, we find out that we can have here. Let's generalize this a little bit more. Actually, we can make this an operator by just factoring phi out, and this is d phi on v. And again, v is a function of phi. And so what does this tell us? This tells us that we can think of any function. We can think of any function that fits this criteria, or that's a solution to this, right? So what does that mean? That means there could be potential multiple functions, or multiple potential functions that satisfy this equation, right? So if we do that, if we say that there's multiple functions that satisfy this, well, we could say that d mu minus m squared phi 1 equals d phi 1 on phi 1, and we can go down to phi 2 d phi 2 on v and phi 2. And we can go down, and so forth, right? And so this ends up, this is very interesting to us. We can see that this potential, again, this function phi defines again sort of the shape of the field that we're looking at, and excuse me, this if we're saying that there can be multiple functions that satisfy this equation, then there can be multiple potentials again that are functions of these different phis, and we can add these up. We can also add these up, right? So we could say that d phi 1 on v phi 1 plus d phi 2 on v phi 2, well, that equals, we're making this stipulation here, m squared phi 1, 2, like that. We can add up the potentials, right? So we can add up the potentials to give us a solution. Because again, we're saying that if this is a solution, if this is a solution to this equation of motion, then, and this is a solution also, we should be able to add them up and also have that work for our equation of motion. Okay. So pictorially, I like to sort of think of this like this. If you're a pictorial thinker, if you think in pictures, we have a function, we have a field, and our field has these delta functions in it. Okay. And this is dv d phi. Okay. And so this is equal to these potentials. Like this. So if we have a field that has multiple excitations in it, and these excitations are interacting with one another, then we can decompose this into different fields that have only one excitation in them. Okay, and this is going to bring us to this concept of delta decomposition. Okay, and this might take us over 30 minutes, and I'm at 20 minutes right now. So have this be a primer on interactions. Okay, this is how we're going to be thinking about interactions. We're thinking about this now in terms of delta decomposition. This delta decomposition, again, this is something that the book covers. And this is really going to help us in understanding exactly what Green's functions are and how they work. So with that being said, I will see you guys in the next one. If you enjoy this kind of content, again, please subscribe. Please visit my Patreon page if that's something you're interested in. And I will see you guys in the next one.